Hello, my name is William Nebinger, and I'm going to talk to you about the Timsort sorting algorithm today. It was developed by Tim Peters in the year 2002, and whether you've heard of it or not, the odds are you've probably used it. Timsort is the built-in sort function for both Java and Python. So if you've ever used an array in Python and done array.sort, or if you've ever done in Java array.sort, you have used Timsort. So I'm going to explain how it works and why they use it, and why it works better than a number of other sorting algorithms. So first, something I need to explain is what hybrid sorting is. So hybrid sorting is basically mixing two different sorting algorithms. So maybe you get some mix of merge sort and bubble sort, or radix sort and some other sorting algorithm, and you put them together, and usually the goal is to make it run faster. So I'm also going to explain something about size of data sets and theory versus practicality. So in theory, we're all familiar with big O notation, and it's pretty trivially, most of us would say, well, insertion sort is worse than merge sort because insertion sort is n squared and merge sort is n log n. But as computer scientists, we know that when we're developing our big O notation, we usually throw away a constant. And so, for example, if we have an algorithm that's 10n squared and an algorithm that's n squared, we get the same big O complexity, but when we actually run really big data on it, the time for 10n squared can take 10 times longer. So basically what happens with like two sorting algorithms, and this is the premise for Timsort, is take insertion sort and take merge sort. Now, insertion sort we know is n squared, but it has very little drag. It has a very little coefficient. So there's not really much else going on except it really just goes through the array in n squared iterations. Not much more than that really happens. It finds the maximum, it goes to the other array, and it continues to do this. Whereas merge sort is a little different. Merge sort might have a higher constant in front of it that changes how the algorithm works on certain pieces of data. So for example, if let's say that t of n, the time it takes to run an insertion sort, is n squared, and let's just say the constant factor is 1. Let's say that for merge sort, we do have n log n time, but we have a higher constant for our time value that gets thrown away in the big O notation. Well, actually, for small pieces of data, for small data sets, it turns out that you can actually run insertion sort faster than you can run a merge sort because of this constant. And so that's where theory starts to argue with practicality. So when Tim Peters was designing his algorithm, he set out to keep an algorithm that had n log n runtime, but it also increased the practicality, not just the theoretical runtimes, but the practicality of the algorithm, so that it would run in a good amount of time, very quickly, on most general sets of data. And I think it's tested, and it pretty much holds up for almost any sets of data. So now I'll explain how it works. So let me start by explaining a binary insertion sort, which is used in Timsort, most implementations. Some will just use insertion sort. But binary insertion sort is basically an insertion sort, but it goes through the list, one element to the next, and it places it into a new array. And it doesn't find the maximum, it just places it into a new array, and if it has to shift elements, it shifts elements to make space for whatever it wants to put in the algorithm. So, to get to how Timsort actually works. So, Timsort basically takes an array, and it chooses the size of partitions that it wants to start its insertion sort. And usually this is strategically chosen to be as efficient as possible. I think the general standard is 64 pieces of 64. But so basically what happens is, say we have an array and we have a million elements, whatever. We look at the first 64, and we'll do a binary insertion sort on this first 64. And then we come over to the next piece, and we'll do another binary insertion sort on this piece. Once this is done, it will merge the two pieces, just like in a merge sort, just no recursion. It merges the two pieces so that we have a sorted chunk. Then it continues on to, you know, the next partition of 64, where it will do another binary insertion sort, and it will merge it with the one following it once they're both sorted. And it will sort these two. And it'll continue doing that throughout the whole array until the entire array is finished sorting. There are some great visualizations on the internet that I encourage you to check out. Go on YouTube, type in Timsort Visualization. Very interesting. You can also check out the source code. The source code is very cool and very useful. Additionally, if you go on the Wikipedia page, it's a great read. And if you go to the bottom of the page where the sources are, there is actually sourced an article written by Tim Peters himself that talks about his motivation for building the algorithm, some results that he got, and how it actually compares in practice against some other well-known sorting algorithms. So I hope that you learned something about Timsort, and I hope you enjoyed this presentation, and I want to thank you for listening. Thank you.